now beginning our major unit on wave theory. Before we confront the task of describing waves, however, we need to investigate what causes waves to be created in the first place. That's the subject of this week. This week we take a look at describing systems that vibrate or oscillate because it's vibrating or oscillating objects that creates waves. As we'll soon see, however, when objects vibrate or oscillate with a special type of motion called simple harmonic motion, a special class of waves gets created. So, simple harmonic motion is a special case of oscillatory or vibratory motion. Let's not get ahead of ourselves, however. Let's begin by being very general here and ask the question, what does it mean to say that an object oscillates or vibrates? Well, we would say that an object oscillates or vibrates when it moves repeatedly back and forth over the same path. Very often we speak about a vibration being a linear motion, okay, like in the case of this mass on a spring, okay, really moving repeatedly back and forth over the same path in a straight line. Okay, while we use the word oscillation to refer to an object that moves repeatedly back and forth over a segment of a circle, like a pendulum, okay, as in the case of our friendly red frog here. So what is it that makes an object move repeatedly back and forth over the same path? It turns out that when the restoring force acting on the object, that is, the force that makes an object want to return to its equilibrium or rest position, okay, when that restoring force is both proportional to the displacement of the object from equilibrium and okay, is opposite in direction of the displacement of the object from equilibrium. Okay, so when these two conditions are met, that is when we can say the object will vibrate or oscillate. We can describe, okay, this state quantitatively as follows. Okay, we can say that the restoring force, okay, is proportional to, okay, the displacement of the object from its equilibrium rest position to some power, and that restoring force is opposite the direction of the displacement of the object from equilibrium. To see what we mean by a restoring force, let's take a look at this simple simulation. Notice that we have a spring that we can apply a force to. So right now the spring is in its equilibrium position as illustrated by this green dotted line, which means that the spring is neither stretched nor is it compressed. Let's see what happens if we exert a force on this spring and displace it from its equilibrium position. So in the first case, I'm going to apply a force, exert a force on the spring, okay, that has a positive value and is going to displace the spring to the right. Let's suppose I apply a force of 50 newtons. So I'm going to check this applied force here in the values box. So this piston applies a force on the spring to the right having a value of 50 newtons. Now you know that by Newton's third law, if the piston exerts a force on the spring to the right, then the spring exerts a force back on the piston to the left that is equal in magnitude and opposite in direction. So right here you see the blue force. This is the spring force, okay, that is the third law reaction force that is acting on the piston. This is what we call a restoring force because it tends to restore the spring to its equilibrium position. Notice here when I check the displacement box that the spring is displaced to the right, okay, a distance of 25 centimeters, but this restoring force that tends to restore the spring to its equilibrium position acts opposite the displacement. It acts to the left.
Let's see what happens if instead of stretching the spring, we now compress it. Okay, so starting here from its equilibrium position, what if we exert a compression force, okay, of negative 50 newtons on the spring? Come on, negative 50. Well, close enough. There we go. Once again, you'll notice here that if the applied force is to the left, so the displacement of the spring is to the left, the restoring force, that is the force the spring exerts back on the piston, is opposite the displacement. It is to the right. This is one of the things that is characteristic of restoring forces. Okay, the restoring force is always opposite in direction to the displacement of the object. A second thing we'll notice that characterizes restoring forces is this. What if we increase the value of the applied force? So right now we have a compression force of 50 newtons, which displaces the spring 25 centimeters to the left. What if we double this applied force to negative 100 newtons? Notice that the restoring force also doubles. Okay, it is 100 newtons. So by increasing the applied force, increasing the restoring force, okay, we have increased the displacement. So you see here the condition for oscillatory motion. Not only is the restoring force opposite the displacement of the object, okay, but the restoring force also increases as the displacement of the object increases. Okay, this is a second feature that is characteristic of restoring forces. The restoring force is opposite the displacement, okay, and it is directly proportional to the magnitude of the displacement.
All right, so let's just take a look at some examples of systems that oscillate or vibrate. So these are just some random examples. Consider a spider web that vibrates back and forth, either under the action of the wind or the spider itself. What is the restoring force in this case? Well, it's the tension in the web itself. Okay, that tends to make the web return to its equilibrium position. Consider a car suspension system. Okay, well obviously the car suspension system has springs, okay, that tend to restore the body of the car to its equilibrium position. Water molecules in the food vibrate in a microwave oven. Okay, what's the restoring force? Well, it's the electrostatic force, that intermolecular force between the water molecules. An oscillating guitar string vibrates, okay, creating a sound wave. Well, it's the tension force in the spring itself. So under some slow motion stroboscopic photography, you can actually see the strings vibrating. A uranium nucleus oscillates before fissioning. Okay, this is in the liquid drop model. It is a nuclear force, okay, that acts as a restoring force in this case. What about air vibrating to create a sound wave? Okay, force resulting from the pressure gradients, okay, in the medium supplies a restoring force. A boat bobs up and down in the water. Okay, clearly an example of an object that is moving repeatedly over the same path. So here, as you learned in your last unit, a buoyant force, okay, can make this boat bob up and down. If we look at bridges and buildings, okay, the elastic compression or expansion forces in the solids themselves can act as a restoring force, okay, to make the different building components vibrate. Vibrating electrons in a wire, creating an alternating current. Okay, well, this is clearly the electromagnetic force acting on those electrons that are forcing them to move back and forth in the wire. Oscillating electrons creating electromagnetic waves. Okay, once again, it's the electromagnetic force acting on those electrons, okay, that causes them to vibrate,
which is a form of an acceleration, which then creates electromagnetic radiation.
Some things to note here. First, most of the macroscopic restoring forces, okay, like many that you saw in the previous slide, including tension, Hooke's law, okay, or elastic forces, are really electrostatic forces on the microscopic level. In other words, they really involve, okay, a force of attraction between oppositely charged particles, like electrons or protons. Okay. Secondly, oftentimes the vibrations are difficult to detect with the naked eye, okay, really for two reasons. First of all, because the amplitude of vibration may be too small, and secondly, because the frequency of vibration is too large. On the next slide, we'll take a look at an illustration of these ideas.
Right, so folks, in about a second, I am going to strike the tuning fork with a rubber mallet. And under normal circumstances, these tines of the tuning fork are going to move back and forth about 256 times a second, which is too fast for the naked eye to see. In addition to that, the amplitude of vibration of these tines is not that great. But under the action of a strobe light, we are going to effectively slow down the motion. So you should be able to see the vibratory or oscillatory motion of these tines. All right, so here goes. Let's strike the tines of this tuning fork. And under the action of a strobe light, you can actually see the vibratory motion of these tines.
In our unit on wave theory, which we'll be investigating next week, we're going to be interested in discussing only vibrations or oscillations that can be considered what we call periodic. So what do we mean by an oscillation or vibration being periodic? We're saying that an oscillation or vibration is periodic when the time required for each oscillation or vibration is constant. We're now going to introduce some kinematic quantities that will help us describe the motion of systems that oscillate or vibrate. Now, if you recall back to your course in mechanics, we introduced a set of kinematic quantities, okay, such as position, velocity, acceleration, okay, whose sole purpose was to allow us to describe the motion of objects in a quantitative way. So in a similar fashion here, okay, these quantities that we're going to introduce are going to allow us to describe the motion of objects that vibrate or oscillate in a quantitative way. So the first quantity that we'll introduce is what we call amplitude, okay, symbolized with a capital A. When speaking about the amplitude of vibration or oscillation, okay, this is simply the maximum linear or angular displacement of our system, of our oscillator, okay, from its equilibrium or rest position. The unit we use to describe amplitude, of course, would be a displacement unit, okay, the SI unit being the meter. When we speak about the period of oscillation or vibration, we're referring to, okay, the amount of time required for one complete oscillation or vibration. The symbol we use to describe period is a capital T. The SI unit, of course, to describe the period would be the SI unit for time, which we all know is the second. Now, think back to your course in mechanics where you talked about uniform circular motion and you saw this concept of period introduced, okay, to describe the motion of objects that moved at constant speeds in circles. And the meaning was very similar. We said there that the period was simply a measure of the amount of time required for the rotating object to make one complete circle. So the meaning here is essentially the same. Okay, we're now speaking about the time required for the object to make one complete oscillation or vibration. The frequency of oscillation or vibration is simply the reciprocal of the period. That is the number of oscillations or vibrations per unit time. The symbol we use to introduce or to describe frequency, okay, there's really twofold. If we're talking about the characteristic frequency, what I'm talking about in this slide, we use the symbol F. And you may recall from your course in mechanics that we also introduce what we call an angular frequency, omega, which is related to the characteristic frequency by this factor of 2 pi. Okay, the characteristic frequency is measured in vibrations or oscillations per second, which we introduce a shorthand unit or called the hertz. When we talk about an angular frequency, as we'll see in an upcoming slide, okay, there we can talk about the angular frequency as being measured in radians per second. As stated in the previous slide, when you think back to your course in mechanics, when you learned about uniform circular motion, hopefully you recall that there was a very simple relationship, okay, between the period of the circulating object and its frequency. Okay, this relationship can be stated as follows, right? The period and the frequency were reciprocals of each other. The period, you recall, is a measure of time, okay, measured in seconds. The frequency is the reciprocal of that, okay, measured in number of vibrations or oscillations per second. So let's take a look at a simple example, okay, to help us get some practice with these kinematic quantities that we introduced in the previous slide. So in this example, we're told, okay, tired of doing homework, a Physics 102 student holds one end of a flexible plastic ruler against the desk and idly strikes the other end, setting it into oscillation. The student counts 30 complete vibrations, okay, for the end of that ruler in a time of 10 seconds, and notices that the end of the ruler moves a total distance of 10 centimeters. So first we're asked to determine the amplitude of vibration. Okay, you recall our definition for amplitude. The amplitude of vibration is simply the maximum displacement of the object from its equilibrium or rest position. So be careful here, because while the end of the ruler moves a total distance of 10 centimeters, that is not the amplitude of vibration. Okay, that is the total distance moved, but the amplitude of vibration is the distance moved from its equilibrium or rest position. So what I'm showing you here, okay, the ruler in its equilibrium or rest position, okay, before it is actually set vibrating, okay, is picture the ruler here that's not colored red. And when you look at the distance between the end of the ruler in this position and either end point, okay, that's the distance that we call the amplitude, 1/2 its total distance. So here we can reason that the amplitude of vibration is going to be 5 centimeters, not 10 centimeters. Okay, we're also asked to find the period of vibration. The period, remember, is the amount of time it takes, okay, for the end of that ruler to make one complete vibration. To begin at one point, move to the opposite end, and come back to the same point. So in this case here, we are told that the ruler makes 30 complete vibrations in a time of 10 seconds. Therefore, the amplitude of vibrations is going to be 10 seconds divided by 30 complete vibrations, or 0.33 seconds per vibration. And finally, okay, if we're asked to calculate the frequency of vibration using the fact that we stated above, the simple relationship between period and frequency, for a period of 0.33 seconds, Okay, the frequency would be the reciprocal of that, the reciprocal of 1/3, which would be 3 vibrations per second, or 3 hertz. So just want to be really clear, period is a measure of time. Okay, that is how many seconds to make one vibration. Frequency is the reciprocal of that, okay, a measure of how many vibrations the object makes per second. So how do we explicitly describe an oscillation or vibration? Well, turns out we have a problem here that we need to address, and the problem is this. Simply specifying the amplitude and frequency of oscillation or vibration is not enough. It's not sufficient to uniquely and completely describe the motion of the oscillating or vibrating object, since two different motions, that is, two different oscillations or vibrations, can have the same amplitude and frequency. What makes two oscillations or vibrations with the same amplitude and frequency different? Okay, the difference lies in the mathematical form of the restoring forces. You recall several slides ago, we said that what makes an object move repeatedly back and forth over the same path is the restoring force. One of the criterion being that the restoring force must be opposite in direction to the displacement of the object at all times, and the second being that the size of the restoring force must be directly proportional, to the size of the displacement. But this leads to a number of possibilities. While the restoring force is proportional to the displacement raised to some power, there are an infinite number of powers or exponents that would satisfy this criteria. So without specifying the exact power, we cannot uniquely describe the oscillation or vibration. So this brings us to the topic of simple harmonic motion. By definition, simple harmonic motion is a special type of oscillatory or vibratory motion that results when a Hooke's law restoring force acts on an object. So as we said in the previous slide, there are lots of different types of restoring forces. To say that the size of the restoring force is directly proportional to the size of the displacement leaves a lot of possibilities. But here we're talking about a restoring force that is linearly proportional to the displacement, and that makes for a special value of the restoring force and a special type of motion that we call simple harmonic motion. So when a Hooke's law restoring force acts on the object, we get the object to move repeatedly back and forth over the same path, with this special type of motion. Let's quickly review Hooke's law, hopefully a law that you learned in your course on mechanics. So as you see here, we have a mass on the end of the spring, and it is free to oscillate back and forth in a horizontal direction. We will start here, with a statement of Hooke's law, which tells us that the restoring force acting on that mass, the restoring force provided by the spring, is equal to minus kx. K being a proportionality constant, x being the displacement of the object from its equilibrium position. Notice here this vertical dotted line. This represents the equilibrium or rest position, of that object on that mass on the end of the spring. That would be when the spring is neither stretched nor compressed, when it's in its equilibrium or rest state. You will notice in the top picture here, when the spring is now stretched to the right, the force that the spring exerts back on the object, symbolized here with F, is opposite the direction of the displacement. So you see here that it satisfies that criteria that the force, the restoring force, has to be opposite the displacement. Similarly, if you look at the bottom picture when the spring is compressed over here, okay, you see that this in this okay, for this position here, the spring would exert a force on the block to the right, okay, giving it a restoring force to the right, whereas the displacement of the block from its equilibrium position is to the left. So once again, okay, in this picture here, it satisfies the criteria that the restoring force is opposite the direction of the displacement. So here, F sub r is what we call the restoring force acting on an object that tends to make it want to return to its equilibrium or rest position. Okay, X is the displacement of the object from its equilibrium or rest position. K is the proportionality constant. In the case of the mass on the spring, we very often call it a spring constant, which would give us a measure of the stiffness of the spring. So a big value for K would represent a spring that is very stiff. A small value for K would represent a spring that is much more flexible. And of course, the minus sign indicates that the force is opposite the displacement. So when we talk about a simple harmonic oscillator, okay, an SHO, this is simply a term we use to describe any object that is subjected only to a Hooke's law restoring force that would therefore lead to simple harmonic motion. Our goal in this slide is to derive an equation of motion for the simple harmonic oscillator. An equation of motion, you recall, is simply an equation that expresses the position of an object as a function of time. And by so doing, that is, if we can get an equation describing the position of an object as a function of time, we can completely describe the motion of the object. So for simplicity here, we're going to consider a special example of a simple harmonic oscillator, and that is going to be a mass attached to the end of a spring, which is free to vibrate back and forth on a frictionless horizontal surface. So how do we get an equation of motion? We get an equation of motion by applying Newton's second law, okay, to our moving object, in this case the mass on the end of the spring. So in order to do that, we'll start by drawing a free body diagram for this mass on the end of the spring. Certainly we have the force of gravity pulling it downwards, and because it is resting on this horizontal surface, it is being supported by, okay, a force we'll call here the normal force, which acts vertically upward. There is no friction in the problem, but if the simple harmonic oscillator, as shown in the diagram, is attached to a spring that is stretched, okay, so this shows you a stretched spring, then we can reason that there is a Hooke's law restoring force acting on the object and the spring, of course, which acts to the left. So we'll describe a two-dimensional coordinate system here in order to adequately describe these forces here, so that we can apply Newton's second law, okay, in a quantitative way. So the left-hand side of Newton's second law simply tells us to sum up all the forces acting on the object. We can reason here that in the vertical direction, the normal force and the weight exactly balance or cancel each other out, such that the net force acting on the object is just this Hooke's law restoring force, okay, which we can write in the form minus kx. Okay, that's equal to the mass times the acceleration. So the equation as it is now written really has two variables, right? Position and acceleration. But you recall that the acceleration is related to position. It is simply the second derivative of position with respect to time. So we will make that substitution here, okay, and say that minus kx is equal to, okay, the mass times the second derivative of position with respect to time. We're going to rearrange that equation a little bit, okay, to write it like this. Now you see we have what we call a second order ordinary differential equation in terms of the single variable x. Our goal is to now solve this equation. Now, many of you are going to be taking courses in, or I should say, a course in differential equations, okay, ordinary differential equations that will allow you to learn very specific techniques for solving certain types of differential equations. This happens to be an ordinary second order differential equation. Second order because it involves the second derivative, ordinary because it involves ordinary derivatives as opposed to partial derivatives. And many of you have probably not taken that course yet where you learn the techniques to actually solve equations of this type. So we're going to rely upon a very old-fashioned approach, an old-fashioned method of solving differential equations, and that is we are going to simply guess at the solution using a little bit of reasoning, of course, here. Okay, so take a look at this equation. Think about it. What does it tell you? It tells you what function x, x is our, a function of position, right? Position is a function of time. It tells you what function x could you differentiate twice and end up getting the same function back again. So we find a function f. On the left-hand side, we differentiate it twice, and then on the right, we get the same function back again, multiplied by a constant. Well, when you think about it, in using your vast knowledge of trigonometry, you would see that by choosing a sine or a cosine function, either one of those functions would fit the bill. We're going to just arbitrarily choose to write our position function as a cosine function, but we could have just equally well as written it in terms of a sine function and end up at the same place. So let's put in some arbitrary constants here. The constant a, the constant omega, and the constant phi here, and we will express our position function as a cosine function. All we are going to do now is substitute this back into Newton's second law. So we're going to need to differentiate it twice. Here I'm just showing you the equation where we've substituted the function in for x. All right, we'll focus on the left-hand side here. Let's differentiate it once. When we differentiate a cos omega t plus phi once with respect to time, we get minus a omega sine omega t plus phi. So that's what I'm showing you substituted in right here. Let's now differentiate it the second time here. And when we differentiate the sine function, we get the cosine function back, again multiplied by the constant omega. So here we have it on the left-hand side. After differentiating twice, this is what we end up with here. On the right-hand side, we haven't really done anything other than substitute in our function x. And lo and behold, we were correct. We see we get the same function back again. Since that exists as a factor on both sides of the equation, we can divide both sides of the equation by a cos omega t plus phi. And when we do so, we find out that omega squared is equal to k over m, or omega is equal to the square root of k over m. So what does this tell us? This tells us that we were correct. Our solution, x equals a cos omega t plus phi, does indeed satisfy this differential equation, satisfies Newton's second law, when this constant omega is equal to the square root of k over m. So either a cosine or sine function of this form is a solution to the simple harmonic oscillator, when this arbitrary constant omega is equal to the square root of k over m. And remember that k and m, these are physical constants for our simple harmonic oscillator. So in conclusion, we can say that the equation of motion for the simple harmonic oscillator we can write as x equals a cos omega t plus phi, where this constant omega is equal to the square root of k over m. Now that we have an equation of motion for a simple harmonic oscillator, that is a function describing the position of the oscillator at any given time, okay, we now want to turn our attention to getting an equation describing the velocity of our simple harmonic oscillator at any time, as well as the acceleration of our simple harmonic oscillator at any time. So, to get the velocity from position, okay, recall that velocity is simply the first derivative of position with respect to time, okay, the time rate of change of position. So by differentiating our equation of motion, a cos omega t plus phi, remember that when you differentiate a cosine function, that gives you a negative sine function. Okay, and when we differentiate the argument of our cosine function, omega t plus phi, with respect to time, okay, we end up with this constant omega back. So A represents the amplitude of our simple harmonic oscillator, okay, a quantity that we described previously, one of the kinematic quantities that allows us to describe the motion of a simple harmonic oscillator. Here we get an expression for the velocity, okay, which is described in terms of the amplitude as well as omega, okay, and what we said on the previous slide, that for any simple harmonic oscillator, omega is equal to the square root of k over m, right? It's related to the spring constant as well as the mass of the oscillator. So it turns out that by knowing a, omega, and phi, the phase constant, which we'll talk more about, okay, in a future slide, we can then find what the position, or now the velocity of that simple harmonic oscillator is at any time, okay, simply by substituting in the specific value of time t. It's of interest here to find the maximum value of the velocity here. And when we look at the function sine omega t plus phi, okay, we know that a sine function oscillates between -1 and 1. So the maximum value of the sine function is 1. Therefore, the maximum value of the velocity would be minus a times omega times 1, okay, or a times omega. As we said, we can also find the acceleration of the simple harmonic oscillator at any time by, okay, taking the second derivative of position or the first derivative of velocity. Since we have our velocity function, let's differentiate it once more to get an expression for the acceleration. So here we differentiate the velocity function, differentiate the sine function, that gives us a cosine function back. Okay, again, when we take the derivative of the argument, okay, we get this factor omega a second time. So we end up with this expression here, minus a omega squared times cos omega t plus phi. Once again, we'll find the maximum value of that acceleration. A cosine function, it too has a maximum value of 1, which will then tell us that the maximum acceleration of our oscillator, okay, would have a value of a times omega squared. Now that we've derived our equation of motion describing the position of the simple harmonic oscillator at any time, and now that we have the resulting velocity and acceleration functions, which will describe, okay, both the velocity and acceleration of the oscillator at any time, let's state the results on this slide and compare and contrast these functions, okay, using the help of the simulation that you see on your screen here. First of all, notice that both the position and acceleration functions are cosine functions, but that the negative sign in the acceleration function, okay, makes it in the opposite direction of the displacement, okay, our change in position. Okay, and remember, the displacement and position really are the same when the initial position of the oscillator is at its rest or equilibrium position. So when we say displacement or position, we're really talking about the same quantity here. The fact that the acceleration and displacement are opposite each other, opposite in direction, should make sense, okay, given that, okay, the acceleration, which would be in the same direction as the Hooke's law restoring force, must be opposite the displacement in order for the object to move repeatedly over the same path. Recall that this was one of the criteria to have a vibration or oscillation, okay, that we talked about in the opening slide. This is what makes an object be able to move repeatedly back and forth over the same path, okay, is when the acceleration and restoring force are opposite the direction of the displacement. Also notice when you look at the functions here that the velocity function is a sine function, okay, where the position acceleration functions are cosine functions, making the velocity function pi over 2 radians out of phase with the position and acceleration of the oscillator. In other words, okay, the maximum position acceleration of the oscillator will occur at times when the velocity of the oscillator is at a minimum. You can see this nicely in the simulation if you trace the red dot as it moves from left to right. Okay, notice that when the velocity has a value of 0, which is right now, okay, the position of the oscillator is at a maximum, what we call the amplitude, and the acceleration of the oscillator would be at a minimum value. Okay, you can also imagine this as well, okay, by looking at the figure that I just, okay, put up on the screen here. This figure shows you the position of the simple harmonic oscillator at various times. And you'll notice that when the position of the block is at its maximum or minimum value, the block is at rest and has no velocity. Okay, conversely, when the block is at equilibrium, x equals 0, you can imagine that it must be moving there. In fact, it must be moving the fastest and have its maximum value of velocity there. Notice too that the frequency and period of all three of these functions is the same. In other words, it would take the same amount of time to complete one cycle, okay, regardless of whether we're talking about, okay, position, velocity, or acceleration. You can certainly see this by tracing the red dot, okay, and notice that as the red dot moves from left to right and completes one cycle, okay, that it does so taking the same amount of time for each of the three graphs.
So remember that our functions describing the position, the velocity, and the acceleration of the simple harmonic oscillator as a function of time were all expressed in terms of these three constants, A, omega, and phi. So let's start by giving them names. Let's talk briefly about what they mean, and then how each of these constants can be determined. Because in order to specify the oscillation, okay, that is to describe exactly what the oscillation or vibration looks like, we need to know values for these three physical constants. So starting with A is what we call the amplitude of oscillation or amplitude of vibration, and it is simply the maximum displacement of the oscillator from its equilibrium position. So this is a relatively easy constant to understand. Now, how would we determine the amplitude? Well, in most of the problems, the amplitude will be given from the description of the problem. For example, if it tells you exert a force on a spring, displacing it a certain distance from its equilibrium position, well, that is the amplitude. For other problems, it may not be given, in which case you can determine the amplitude from the set of initial conditions. We'll talk about how to do that in a problem on the next slide. So moving on, this constant phi is what we call the phase constant, sometimes called phase angle. What does phi tell you? It really tells you how long before or after the start of the problem at time 0, the peak, okay, the maximum amplitude is going to be reached. In other words, when will your oscillator be at its extremes, okay, at a maximum amplitude or minimum amplitude? So when there is no phase angle, when the phase angle or phase constant has a value of 0, then that basically tells you that you start the problem with your oscillator at its maximum amplitude. Okay, but if you have a phase constant other than 0, it tells you no, sometime later, okay, the oscillator will be at its extreme point, will be at a position of maximum or minimum amplitude. Once again, this phase constant, if it's not given to you in the problem, it can be determined from the set of initial conditions. And finally, let's take a look at the constant omega, which is what we call the angular frequency. Now, remember we said that omega, when we looked at our simple harmonic oscillator, our equation of motion, that our generalized expression for that function satisfied the differential equation when omega was related to these constants, the spring constant and the mass, okay, by this specific relation of the square root of k over m. So for most problems, that's how it's going to be determined. Okay, you will know the spring constant, you'll know the mass, and so from that you can determine omega. I want to show you here, though, the relationship between omega, this constant, and the period of oscillation or period of vibration. So we are assuming that when we have a simple harmonic oscillator, that the position is a periodic function, and so is the velocity and acceleration. In other words, okay, saying that this oscillator moves repeatedly back and forth over the same path, okay, means that the position will repeat itself in a periodic or regular fashion. We can say that the position will repeat itself, will be exactly the same for your oscillator, okay, when this phase, that is omega t plus phi, changes by 2 pi radians. So you know this from trigonometry. We can also say that the oscillator, if it's in a given position at one time, it will be in exactly the same position, okay, one period later, at a time equal to, you know, that time plus, okay, whatever the period is. So these are really two ways of saying the same thing, that when we look at our equation of motion, we're saying that our oscillator will have a given position, okay, a cosine omega t plus phi. If we change that phase by 2 pi radians, okay, that would be completely equivalent, doing that on the left-hand side, as changing the time by 1 period on the right-hand side. So these two expressions here give us exactly the same position for the simple harmonic oscillator. So if we simplify them and cancel out our common terms, we find out this relationship that omega t is equal to 2 pi, or writing a little bit differently, omega is equal to 2 pi over the period. So we see this relationship between this constant, the angular frequency, and the period t. This is the same relationship you saw when you studied uniform circular motion in mechanics. Okay, you saw that there was a relationship between the frequency and the period as well. Like we said before, in order to determine omega, it's typically in most problems determined from these constants in the problem, the spring constant and the mass, which will be given to you in the problem. All right, so let's take a look at an example problem and see how we can go about finding these constants A, omega, and phi. Because remember, describing the equation of motion, okay, that is the position as a function of time, means we need to find the values of these three constants, A, omega, and phi. So here's the problem we'll take a look at. We're told that a 0.5 kilogram mass on the end of a spring having a spring constant of 200 newtons per meter is set in motion along a horizontal frictionless surface. If the initial displacement of the mass is 0.015 meters and its initial velocity is 0.4 meters per second, determine the position, velocity, and acceleration of the mass as a function of time. So here, okay, for these three physical constants, the easiest thing to do is to start by calculating omega, because remember, that is related to the spring constant of mass, and both of those are given to us in the problem. So we now know that omega is equal to 20 radians per second, okay, or 20 seconds to the -1 power. Now, to find the other two constants, that is A and phi, we're going to get that from the initial conditions. Okay, it basically is going to amount to solving two equations and two unknowns. Now notice here in the problem it says if the initial displacement of the mass is 0.015 meters. So we are given the initial position of the mass. We're also given the initial velocity of the mass. So by using the equation of motion here, our A cosine omega t plus phi, okay, and when we talk about an initial condition, we mean at time zero. So we're told that right at the start of the problem, at time zero, our oscillator, okay, the mass, has a position of 0.015 meters. So let's plug in 0 for time, and now we know that x, our position, has a value of 0.015 meters. So when we simplify this, this gives us an equation, one equation, two unknowns here. Okay. Notice in this problem, I just want to point out that you cannot assume that at the start of the problem your mass will be at a maximum displacement, or let's say the amplitude of your oscillator. You cannot assume that. Okay, the second initial condition we have is information about the velocity of our oscillator at time zero. So using our general expression for the velocity function, minus a omega sine omega t plus phi, plugging in a time of zero, at time zero we know the velocity is 0.4 meters per second. So plugging in 0, we know the velocity has a value of 0.4 meters per second. And when we simplify that, notice that once again we have one equation, two unknowns, but they're the same two unknowns as we had in the equation above for our equation of motion. Okay, so right here, this equation, two equations expressed in terms of the same two unknowns. So we basically just have to solve the system of two equations, two unknowns. There's more than one way to do this, but perhaps a simpler way to do it would simply be to divide one equation by the other. So if I divide the second equation for the velocity by our equation of motion, notice what happens. The A sine phi over A cosine phi, A's cancel out, and the sine over the cosine gives us a tangent. So we find out that the tangent of our phase constant is minus 1.33. And we can solve that. And notice here that because, okay, the sine of, okay, that angle is negative and the cosine is positive, although the tangent function gives you two solutions, two possibilities, this tells us that our solution, okay, out of the two solutions, that is, okay, quadrant 2 or quadrant 4, we know that our angle has to be in quadrant 4 because that is where sine, okay, has a negative value and cosine has a positive value. So basically our phase angle then we can solve and find that that's minus 53.1 degrees or minus 0.93 radians. Once we know that, we can back substitute to find out what the amplitude is. So just plugging into this first equation here, A cosine phi equals 0.015. Now that we know phi is minus 53.1 degrees, we substitute that in and we find out that our amplitude is 0.025 meters. So notice that the position of our oscillator when we start the problem, it's only at 1.5 centimeters, but the maximum displacement, the maximum, our amplitude is 2.5 centimeters. So from here, we can write down our three equations describing this oscillation. So our equation of motion, okay, A cos omega t plus phi, we know what A, omega, and phi is. We can substitute that in. Okay, our velocity equation, once again expressed in terms of these same three constants, we plug in those values and we do the same for acceleration. And now we have completely and uniquely described this simple harmonic oscillator.
Let's now spend a little bit of time exploring some of the factors that will affect the period of the simple harmonic oscillator. We'll start by taking a look at the spring stiffness, or should I say elasticity constant, okay, that we call K. Remember that in deriving our equation of motion for the simple harmonic oscillator, okay, we found that the constant omega was related to both the spring constant and mass, okay, as follows. Okay, remember omega was equal to the square root of K over M. We said that when we guessed at the solution of the for the equation of motion of the oscillator, okay, we had this arbitrary constant omega, and we showed that when omega satisfied this condition that is equal to the square root of K over M, okay, that proposed solution or guess solution was indeed a solution for the simple harmonic oscillator. Okay, the constant omega is a measure of frequency, the angular frequency of the oscillator to be exact, okay, which is related to the characteristic frequency f by the factor 2 pi. So if omega is equal to 2 pi f and f is the reciprocal of the period, okay, we can then say that omega must be equal to 2 pi divided by the period. Okay, and solving this for period, we find that the period of the simple harmonic oscillator goes like 2 pi times the square root of m over k. Okay, so you can see from this equation here, okay, that the period is directly proportional to the square root of the mass of the oscillator. Okay, this tells us that as the mass of the simple harmonic oscillator gets bigger, okay, the period increases as well, meaning it would take the simple harmonic oscillator a greater amount of time to complete one oscillation. So in the next slide, we'll take a look at a simulation, okay, to see exactly this, okay, the effect of the spring constant or elasticity constant on the period of the simple harmonic oscillator.
Let's take a look at a simple simulation to see how each of these factors, that is spring stiffness, amplitude of vibration, and mass, will affect the period of the simple harmonic oscillator. Starting with spring stiffness, we'll conduct a controlled experiment, or rather, should I say, controlled simulation. So we're going to start by choosing the same mass to put on each of these two springs. We'll choose a 100-gram mass. And we will control the spring constant. So the spring on the left, okay, will represent a very flexible spring with a small spring constant, whereas the spring on the right will represent a very stiff spring with a large spring constant. Let's take out a timer here, and we are just going to visually examine the period of each of these springs. After looking at this for a while, hopefully you see that the period of vibration, that is the amount of time it takes for the spring to make one complete vibration, one complete oscillation, is clearly different for these two springs. Notice that the flexible spring on the left has a much longer period of vibration than the stiff spring on the right.
So what can we conclude from the simulation that we just witnessed? Was the observed relationship consistent with what theory told us we should expect to see? Most definitely. Okay, we saw that for the case of the stiff spring, okay, with a large value of K, the frequency of vibration was large, okay, as theory would suggest, direct relationship between omega and K. That is, we saw a large number of vibrations per second compared to the flexible or not so stiff spring, okay, and the period of vibration was much smaller, okay, meaning that it did not take very long for the mass on the end of the stiff spring to make one complete vibration. Okay, let's now turn our attention to the question of amplitude and ask how does the amplitude of oscillation, amplitude of vibration affect the period? Well, let me ask you this. Do you observe any amplitude dependence in any of the equations? Certainly not in the equation you see above. Okay, the amplitude is not part of that equation. Well, let's take a look at a simulation to see if this is indeed the case.
In this second simulation, we'll see how the amplitude of vibration affects the period of the simple harmonic oscillator. So to run a controlled simulation, we'll keep the spring stiffness constant for both springs. We'll also keep the mass constant for both springs. So let's put 100-gram mass on each of the springs. And we will control the amplitude of vibration by stretching one spring further than the other spring from its equilibrium position, which is shown to you here with the green line, okay, before releasing each of these springs. All right, so notice we have the same mass on each spring. We've got the same spring constant. The only difference in the simulation is the amplitude of vibration. Let's release both of these springs and visually examine, okay, how these differing amplitudes will affect the period of vibration. So hopefully you see that clearly the amplitude of vibration is much greater for the spring on the left, but if you'll notice, their periods of vibration are identical. It takes each of these springs, or I should say each of these masses, the same amount of time to make one complete oscillation.
So, is our experimental simulation consistent with theory? Yes, sirree, Bob. We see that, okay, in answering the question, how does the amplitude of vibration affect the period? We saw in the simulation that it doesn't. Okay, and this is consistent with our equation for frequency and period, which shows absolutely no amplitude dependence. Okay, and finally, let's now take a look at how the mass of the simple harmonic oscillator should affect the period. Clearly, we can see in the equation here that there is a direct relationship between the two, right? That the period of the simple harmonic oscillator goes like the square root of mass. Let's check out another simulation and see if this is indeed the case.
So the last factor we'll look at in the simulation is that of mass. In other words, how does the mass on the end of the spring affect the period of vibration? So to run a controlled simulation, we'll need to keep the other two factors, that is the spring constant as well as the amplitude of vibration, fixed. So let's start by placing a small mass, a 100-gram mass, okay, on the spring on the left, and let's take a look at its equilibrium position here. We'll start it out in equilibrium. And we will place a much larger mass, a 250-gram mass, on the spring on the right, and once again start it out in its equilibrium position. So we will start the simulation and we will visually take a look and see how the mass on the end of the spring affects the period of vibration. So hopefully you all agree here that the mass on the right, okay, the spring with the larger mass, has a greater period of vibration. It looks like there is a direct relationship between the mass on the end of the spring and the period of vibration, the amount of time it takes for the mass in the spring to make one complete vibration or one complete oscillation.
So as the simulation clearly illustrated, all is alive and well in SHM land, right? We saw that as the mass of the simple harmonic oscillator increased, the period increased as well, okay, in accordance with our expectation. And finally, let's consider a sample problem where we combine many of the kinematic concepts introduced thus far in the video. So in this problem, we're told that in a testing device, a spring stretches 0.15 meters when a 0.3 kilogram mass is hung from it. The spring is then stretched an additional 0.10 meters from this equilibrium point and released. So first we're asked to determine the spring constant. Okay, well, we have enough information to use Hooke's law to determine the spring constant, right? We're told that when a weight or mass is hung from the spring, okay, we know how much that force, that weight, stretches a spring. So we can plug it into Hooke's law. When a force given by 0.3 kilograms times 9.8 meters per second squared, that is the weight of the mass. Okay, it's hung from the string, it stretches the spring 0.15 meters from its equilibrium position, okay, giving us a spring constant, okay, having a value of 20 newtons per meter. Next, we're asked to determine the angular frequency of the oscillating system. Remember that we said for simple harmonic motion, there is a simple relationship between the angular frequency of the simple harmonic oscillator, okay, and the spring constant as well as mass, okay, that omega goes like the square root of k over m. We know k, we figured that out from the first part of the problem, divide through by the mass, okay, we are done. We get a value of omega of 8.2 radians per second. Remember, the radian is a unitless quantity. We can add it in there for omega, but technically it has no units. Next, we're asked to determine the characteristic frequency of the oscillating system. And we know that the angular frequency omega is related to the characteristic frequency by the factor 2 pi. That omega goes like 2 pi times f. Solving for f, okay, that is the ratio of omega over 2 pi, given the fact that we know omega from part 2, okay, 8.2 radians per second divided by 2 pi radians, okay, gives us a value of 1.3 hertz. Next up, we want to find the period of oscillation. Okay, well, we know that the period and the characteristic frequency f are simply reciprocals of each other. So given the fact that we now know the characteristic frequency is 1.3 hertz, take the reciprocal of that, we get the period of 0.77 seconds. Finally, it says determine the amplitude of oscillation. While no calculations are required here, you've got to be careful. Okay, in this problem, okay, we're told that when a 0.3 kilogram mass is hung from the spring, it stretches 0.15 meters. At that point, okay, the spring would be in equilibrium. Okay, in other words, the weight pulling the spring and mass downwards, okay, would be exactly equal and opposite to the restoring force, okay, acting on the mass provided by the spring pulling it upwards. So that 0.15 meters is not the amplitude. The mass and spring are not yet oscillating. The oscillation starts when we now pull the spring and mass down an additional 0.1 meters from its equilibrium position. Therefore, it's the 0.1 meters, okay, that is the displacement or the stretch from the equilibrium position that is the amplitude. At that point, once we've stretched the mass of spring that additional 0.1 meters, we have not released it yet, but once we do so, once we release it, we now set the mass and spring into vibration. In the next part of the problem, we're asked to determine the equation of motion for the oscillating system. That is, okay, the position or the displacement of the spring as a function of time. As I said previously, remember position and displacement are exactly the same if the initial position, okay, is taken to be 0. So let's start by defining a coordinate system here, because we notice that when we find an equation of motion, position and displacement, these are vector quantities, so we need to talk about the direction here. Notice that our mass and spring are initially displaced downwards, which according to my coordinate system is in the negative direction. So say here the motion begins at a point of maximum displacement downwards, and as we said, if we take downwards to be the negative direction, then the initial position, that is position at time 0, okay, would be negative 0.10 meters. 0.10 meters being the amplitude, okay, and the negative sign tells us what the position of vector quantity is right at time 0. So starting with the generalized equation for the position of any simple harmonic oscillator, A cos omega t plus phi, let's plug in the information we know. So we say here at time 0, when the time is 0, the amplitude is 0.1 meters. Okay, we found omega in the previous slide to be 8.2 radians per second. And we're going to plug in a time of 0. The constant phi is unknown at this point, but we know that at time 0, that initial position has a value of negative 0.10 meters. So we're going to plug that in, and in that case, from our initial conditions here, we're going to be able to find that phase constant, okay, phi. So solving this here, okay, we see here that the 8.2 radians per second times 0 gives us 0, so we end up with an argument of simply phi, taking the cosine of phi, dividing both sides by the 0.10 meters, gives us the fact that the cosine of phi is negative 1, in which case we can reason that phi must have a value of pi radians. So now we know all three constants in our equation of motion, A omega phi. We now can write it down. We can say then that the position of our simple harmonic oscillator as a function of time is 0.1 cos 8.2 radians per second times the time plus pi. So you see here we have a function describing the position of the oscillator, okay, at any time t.
And lastly, we'll be asked to determine the velocity of our oscillator as a function of time, as well as the acceleration as a function of time. And in part 7 of the problem, we're asked to actually evaluate the velocity at a particular time of 0.15 seconds. So let's start by finding the general expression, which is a matter of plug and chug. Once we've determined these constants A, omega, and phi, okay, we know that our general expression for velocity is minus A omega sine omega t plus phi. Plug in the values for the constants. Okay, and at a time of 0.15 seconds, we'll plug in that value of time. Make sure when you evaluate this that your calculator is set to radian mode, okay, Make sure that when you find omega, it is going to be expressed in terms of radians per second. So you need to make sure that your calculator is in radian mode as opposed to degree mode. And when you do the number crunching, you find out that your velocity should be 0.77 meters per second in the positive or upwards direction. Lastly, we're asked to determine the maximum acceleration of the oscillating system. So our general expression for acceleration looks like this: minus omega squared cos omega t plus phi. Remember that the cosine function oscillates between 1 and -1, so its maximum value is 1. In other words, the maximum acceleration is simply minus a omega squared. The amplitude and angular frequency are given. So we plug in those numbers, and after doing the number crunching, come up with a value of 6.7 meters per second squared for the acceleration. The maximum acceleration, excuse me.